Welcome back, Science 10 gang. This video deals with the 10.3 little booklet section that I gave you, defining acceleration. So we looked at that a little bit already, talking about what acceleration is. It could mean speeding up or slowing down. It doesn't have to be necessarily speeding up. Just in general, a change in speed over a change in t, like that formula there suggests. Really, these are the two, except this one tells you a little bit more information, indicating that it's average acceleration. And we kind of ran through this already. I think this is the same exact example we ran through before, and dealing with the units of meters per second, or combining them into meters per second squared, taking seconds multiplied by seconds to get seconds squared. Okay, so you can read through this first sheet if you like and get a better idea. Here they just once again talk about the relationship between units. Meters per second is the same as meters per second squared, etc. And here they have a little example, and I think it's the same example that we ran through earlier as well. So if we look at a sample problem here, Miriam Bedard accelerates at an average of 2.5 meters per second squared for 1.5 seconds, as indicated in the diagram over there. What is her change in speed at the end of 1.5 seconds? So like any problem that we've done previously, make sure you write down all the variables. So right here, for example, accelerates at an average of 2.5 meters per second squared. Once you see meters per second squared, that indicates acceleration. So we in fact know what A is, what the acceleration is. And we're told that this happens for 1.5 seconds. Of course, that's time. And lastly, what is her change in speed? What is the change in speed? So that is the question mark. That's the key to solving these problems. Writing down what you know, and then writing a question mark by the information that you don't, or the variable that you don't know, and then working it that way. Now, if we go back, think of the old triangle of terror here. So we have AAV equals delta V over delta T. And of course, in this question, we're looking for V. So what do you do with the variables A and T? We're going to multiply them. So you'll never get it rearranged incorrectly if you think of this triangle and how that all comes together. So delta V is equal to average acceleration multiplied by time. So if we substitute those values in, we'll have 2.5 meters per second squared multiplied by 1.5 seconds. And if you notice carefully here at the units, one is this seconds cancels with one of the seconds that are on the denominator here. So we'll end up with meters over seconds, which is a unit for speed. So if you multiply that out on your calculator, delta V equals that. Let's see here, what do we get? We get 3.8. 3.8 meters per second. Easy enough there. Key thing there, write down what you know, figure out what you're asked for, use the triangle there to figure out which variable we need and how, in fact, to do that. 3.8 meters per second. Next example, sample problem 2. A skateboarder rolls down a hill and changes his speed from rest to 1.9 meters per second. If the average acceleration down the hill is 0.40 meters per second squared, for how long was the skateboard on the hill? Now, this one is sneakily looking at change in speed in terms of talking about going from 0 to 1.9 meters per second. So really, that is a change in speed. From 0 to 1.9, the change in speed is a difference of 1.9 meters per second. And we're also told the average acceleration. AAV, 0.40 meters per second squared. And of course, for how long was the skateboard on the hill? For how long? That's insinuating time. So that's the big question mark right there. So, thinking back to the triangle of terror here, we have average acceleration equals change in speed over change in t. And of course, we're asked to find t here, so we can see how to manipulate it by using this triangle. Can't go wrong with pyramid power. So delta t equals delta v over AAV. So change in t equals my speed, which is 1.9 meters per second, over 0.40 meters per second squared. Now the units are kind of funky here and tricky. The funkiness, so the meters cancel. One of the seconds cancels with one of the seconds. We're left with the seconds that's on the denominator of the denominator. So what happens there is that we take the reciprocal of that and multiply. So actually the time does work out to be seconds. It's tricky manipulating that. But if you have your speed in meters per second, acceleration in meters per second squared, that'll leave you with seconds as a final answer. And let's see here, we get 4.8 seconds when you actually put that into your calculator there. So a little bit tricky, and here they kind of showed over here, if you want to look at the box here, the manipulation and showing how you end up with seconds. They take the meters per second in the denominator, invert, multiply. It's something you would have hopefully taken in one of your math classes, and that's how we get the units to work out nicely there. Okay? Then looking at the bottom here, they talk about refining the acceleration equation. So if we know that change in speed is v2 minus v1, or final speed minus initial speed, we can think of it like that. Or think of the equation as v2 minus v1 over delta t. Okay? We're not going to go too in-depth into that. We're just going to do somewhat easier examples in which we're given the initial speed, final speed, and we're asked to figure out the change in speed, as you'll see here. Karen Lee Gardner is moving at 1.8 seconds near the top of a hill. 4.2 seconds later, she is traveling 8.3 meters per second. What is her average acceleration? So, what is average acceleration? That's what we're asked to find. So I'll write AAV equals big question mark. So that's what the question's asking us to find. We're also given a time period there, 4.2 seconds. 4.2 seconds. And that must mean that we should be able to calculate change in speed quite easily. And what they do here is we have initial and final speed. So we can think of delta V as V2 minus V1. Which in our case, you were going, or she was going at 1.8, and then sometime later, time passes, you're going 8.3. So the final speed is 8.3. The initial speed, or V1, was 1.8. So be careful. It's always this final, the last speed minus the first speed. So here we'll have 8.3 meters per second minus 1.8 meters per second. Of course, if you're running out of room on your page, just press extend to page like I do here, and you'll have more room on your paper. So when we figure that out, find that difference in speed, we could just put this all in the big formula here too. No, it's our usual way of representing it. VAV equals delta V over delta T. And of course, we have delta V can be represented as V1 over, or sorry, V2 minus V1 over delta T. And then put all this in here. 8.3 meters per second. So you could have done this before. It doesn't really matter. All over our time period of 4.2 seconds. I'm going to have to press extend to page there again. And if you type in your calculator, so do the subtraction, then divide it by 4.2 seconds. Let's see here. Our A works out to be, I got it figured out here earlier, 1.5. So run through that and see if you get that. Now 1.5 meters per second, or of course that can combine and give you that. Okay, so relatively straightforward. Now you could have done this here, figure out 8.3 minus 1.8, get your answer, put that answer here, then figure out, or just combine it into one big formula and work it out that way. It doesn't matter. Okay, I think I have, let's see here, one more example here. Acceleration while slowing down, just to show you that acceleration doesn't necessarily mean speeding up all the time. So in a race, a car traveling at 100 kilometers per hour comes to a stop in 5 seconds. What is the average acceleration? So average acceleration is what we're looking for again. Initially going 100, so that's V1. Coming to a stop is V2, of course that's 0. And change in time is equal to 5 seconds. So our change in speed is V2 minus V1. So as you can see here, our final V2 is 0. Our initial V1 is 100 kilometers per hour. So if we use our average acceleration formula, change in speed over change in t, so V2 minus V1 over delta t, and in our case, our final speed is 0 because it's coming to a stop. Our initial speed is 100 kilometers per hour, which is fine. You can do 0 minus 100, you get negative 100, right? And this is all in 5 seconds. So when we figure that out, we have 0 minus 100 divided by 5.0 seconds. So you'll actually get negative 20 kilometers per hour. And here we have to use the funky unit of kilometers per hour per second. We can't combine the two time periods because our time, we're dealing with times of hours in our speed variable and seconds in our other one. Okay, so negative 20. The negative means slowing down. Okay, so those are some examples dealing with the acceleration equation. If we look further here, the questions I want you to do here, we can omit 1, 2, and 3. So let's do that. So I think we're okay with that. So 4 and 5, we'll do those ones, or you'll do those ones using the formula. 6, we'll omit that. 7 and 8 you should be able to do. And then on the next page here, number 9, you should be able to handle that one. We'll omit 10, 11, and 12. And then lastly, end up with 13 and 14. And those questions are very similar to the ones that we've done here, as you can see. So use the acceleration equation, be able to manipulate it. This is the key right here. Use that triangle there to really help you out. And of course, read the question, write down the variables you're given, write down a question mark by the variable you're asked to find, and then using that triangle or pyramid, you should be able to figure out the unknown.